So let's look at the phenomena of thin films. Again, if you look at like a CD, there's a little coating on the CD which kind of produces this little effect of the rainbows. Alright, let's say you have a layer of air, and let's say down here you have glass, and then in between you're going to put a layer which we would call a thin film or a coating on the film. Let's say that n equals 1.5. Okay, actually let's just do a little bit of review first. Let's say you send in some light like this. What happens when you go from air to a different index? Slows down, and then what happens to it? It refracts. How should the angle refract? As remember, it's a review question, a good conceptual question. Does it bend towards the normal or away from the normal? Towards. So this would bend towards the normal, smaller angle, right? Now there's something else that happens that I didn't really talk about at the time, but not only does it go through, not only does it refract, but it also reflects. So there's actually two things that happen. You get some refraction and you get some reflection as well, both of these. Now this you've experienced all the time. Anytime you look through a window, you can see through the window, but what else can you see? A reflection off the window. Even if you look in the classroom, you look through the cabinets, you can see through the cabinets, but you can see the reflection off the cabinets. If you look in like a swimming pool or something, you can see through this pool, you also see the reflection of the sky off the pool, right? So anyway, that you get this double thing that happens. Okay, today we're not going to look at this complicated of a problem. We're going to look at a simpler one, which would mean, which is if I just come straight down like this. So if I just come straight down, some of the light's going to continue, and some of the light's going to reflect. Now at the second boundary, some of the light's going to continue, and some of the light's going to reflect. And actually this will continue. This will like reflect, transmit, reflect, transmit over and over again. But we're just going to look at these two beams. So the first one reflects off the first boundary, and the second one reflects off of the second boundary. Okay? And so let's say we were looking at these two beams of light. Let's say this is my eye here, and I'm looking at these two beams of light. Okay, maybe I'll do different colors or something. So the first one is black, the second one will make it purple. It doesn't really look purple. Oh well. So we have the second one is purple, the first one is black. So anyway, when these two beams come together, notice they are traveling two different distances. Which one's traveling farther, the purple or the black? The purple one. Yeah, the purple one's traveling farther because the black one's just going up and back, and this one's going all the way down and back up. Okay? So here's the whole concept of the day. What if the second beam travels exactly 1/2 of a wavelength farther? The second beam travels exactly 1/2 of a wavelength farther than the first beam. What would happen? Wouldn't travel at the same distance. So beam number 1 travels like this, a certain distance. Beam number 2 travels exactly 1/2 a wavelength farther. So when they come back together in my eyes, what would happen to the two? Crest on trough, trough on crest, what would happen to them? They would destroy each other. Exactly. Okay? In other words, if I were to look at this, let's say I sent in a laser and that laser reflected exactly a half wavelength farther, I would not see a reflected laser. It would just be black. When I looked at it, it would just be black. Okay, so destructive interference, which means it'd look dark. Okay, well, you could probably write the second sentence for me. What am I going to say on the second sentence? What if the second beam travels what? Well, it can't travel the same. The purple one has to go farther. One full wavelength. Okay, so in other words, first beam travels like this, second beam travels a whole wavelength farther. What happens when it gets together? Constructive interference. In other words, what would I see? A very bright light, right? A very bright light. So examples of this would be like, for example, let's say you have those kind of sunglasses where you look at them and they're kind of tinted a color. They tint them like blue or red or something like that. Basically, they put a coating on there so that when it reflects back, it's exactly one full wavelength farther or more. It doesn't just have to be one. Can you think of other situations besides one? 2 or 3 or 4 or 5 or any whole number, right? Any whole number this will happen. What about this? 1/2 or 3/2 or 5/2 or any half number wavelengths. So anyway, if you have those special sunglasses where they look blue, basically they construct the coating so that when it reflects back, the blue one dominates, and you see that blue color. That's the one that pops out at you. Okay? Or this might be if you have anti-reflection coating. They sometimes call it anti-reflection coating. Like, let's say you're a sniper in the jungle. Okay? You're hiding out in a tree. However, if you just had a regular old glass sniper scope, what would happen? As you're sniping someone, they would see the little reflection of the sun off of your glass, and if they see some weird reflection in the tree, what do? They just start shooting in the tree, right? So you put this coating where when it reflects off of it, you get destructive interference, and therefore the sun, it is reflecting, but it destroys itself, and therefore you can't see it. Okay? All right, so the task for today then is to figure out to figure this out. So how do we find, if you're an engineer, how do we find the thickness of our coating? If you want your sunglasses to glow red, what thickness should you make it? If you want to create anti-reflection coating, what thickness should you make it? So that's what we're going to look at today. Okay, so here's the task. So let's title this, How to Find the Thickness. How to find the proper thin film thickness. Okay, alright, so let's start with kind of the equation for this. So let's do for destructive interference. And I'm going to elaborate on the equation, but let's just start with where we began. So first of all, just conceptually, if this is thickness, we'll call that T. How much farther is the purple one traveling than the black one? Two T, right? So purple one has to go down a distance T, and then back up a distance t. So the total distance it travels is 2t. So we're going to start with that. So we're going to say, well, for destructive interference, I would want 2t to be equal to what? What should the path difference be? 1/2 of a wavelength, right? Destructive interference, you want that path difference to be 1/2. Okay, actually I'm going to write this a little differently because as it turns out, it's not quite this simple. So leave a space, okay? So we're going to write 2t equals 1/2 of a wavelength. Now it doesn't just have to be a half. What else could it be? 3/2, or what else? 5/2, etc. Now they will often ask you for the minimum thickness, in which case you'll use the smallest one, in which case you use 1/2. Most of the time you'll just use 1/2. Alright, what about for CI? We want 2t. Now leave yourself a space. It's not as simple as it seems. 2t is equal to, when do we get constructive? A full wavelength. Or 2, or 3, etc. So we're going to start with that, and that's kind of the concept I've just been explaining to you. Let's call this step 1. Okay, step 2. Yeah.
I don't understand the T's.
T is the thickness. So remember I said we want this to travel, we have the black one going like this, and you have the purple one going like this. To get destructive interference, you want the second beam to travel 1/2 of a wavelength farther. That will create destructive interference. So notice the exact distance it actually travels is, it goes down a distance, the thickness of the coating, and then up the thickness of the coating. So the actual distance it travels is twice the thickness of the coating. And you want that 2t then to be equal to 1/2 a wavelength. That will produce destructive interference. Okay, second thing. Now notice I have a wavelength here. However, and we discussed this earlier when we talked about the lab, notice I actually have 3 different materials. I have my air, I have my coating, and I have the glass. So the question is, oh, I made a mistake here. Sorry. Can you guys correct this? This should not be 1.5. Let's make this 1.8. So anyways, we have 3 different substances. We have the air, we have the coating, we have the glass. Which wavelength am I talking about? The wavelength in the air, the wavelength in the coating, or the wavelength in the glass? The wavelength in the coating, right? So this is the distance. We're looking for the thickness when it's traveling through the actual coating. So number 2, make sure you use the wavelength in the coating or film. Sometimes they call it a coating, sometimes a film. So you're going to have to calculate that. We did that in the last unit. We'll do an example problem and just kind of do it again if you forgot how to do it. Okay, question number 3. Step number 3. You have to find what's called the net phase change. Find the net phase change. So phase change is, well, recall when we talked about waves. If I sent a wave pulse down a slinky, and I did this for you, sent a wave pulse down a slinky, when it hit the fixed end, it reflected. Now how did it reflect? It inverted. Right? This is called a phase change. When it inverts, meaning the crest all of a sudden becomes a trough, that's called a phase change. So it inverts like that. So what you're going to do is you're going to try to identify what's the net phase change on the reflections. Because if you go back here, how many reflections do we have? Or how many are we looking at? We have this first one here, and we have the second one here. So we're going to look at whether there's a phase change on either of these, and then find the net phase change. So here's how you figure out whether there's a phase change. We'll just follow the rules here. Letter A, if N1 is less than N2, in other words, if you go from a small n to a large N, then there will be a phase change. And the phase change is exactly a half a wavelength. So in other words, if you think of it this way, this is a crest, this is a half of a wave, right? And it changes by a half of a wave. So the crest becomes a trough. So we're going to have a half of a phase change. Okay? You could probably write B for me. What am I going to say on B? If what? Yep, if N, actually I didn't want to start with N2, let's start with N1. If N1 is greater than N2, so in other words, you go from large N to small n, what do you think? So if you go from a large n to a small n, there's no phase change. So in other words, the crest would just come down and it would stay a crest. So it would just kind of go like this and reflect back like this. No phase change at all. Okay, so then we're going to find the net. So basically we're going to find the phase change on both boundaries. Both reflections. So look at it on both boundaries and then find the net. PC stands for phase change. I'm just tired of writing phase change, phase change, phase change, phase change. PC. Find the phase change for both reflections and then find the net. So what are the possibilities for there's only 3 possibilities of what could happen. Possibility number 1 is there's no phase change on both. What's the net then? 0. You can either have a phase change, then the net phase change, PC net, equals 0. Okay, what's another option? One has a phase change. Okay, so either the top boundary or the bottom boundary, doesn't matter. One has a phase change. What's the PC net? Well, if the top flips by a half and the bottom doesn't flip at all, what's the net result? A half. So lambda over 2. And the final thing, what's the final possibility? Both. do you think? Okay, so lambda over 2 plus lambda over 2 equals lambda. Or 0. You get your choice. Whichever one you feel more comfortable with, lambda or 0. The reason it can be 0, let's look at it this way. Let's say I have my two waves, okay, and they're both coming in, they're both oscillating the same way, right? If one flips like this, now they're in opposite directions, so that would be you'd account for the half. But if they both flip, notice they're back in the same direction, so you don't have to account for the half. So either there's one full wavelength, or since they're both in the same direction, there is no net phase change. They're both moving the same way. So you can use either one, whichever one makes more sense to you. Just use it that way, and that will they both work. So let's go back to original equation. We're just going to take this and we're going to add our PC net. So our full equation for DI looks like this, destructive. And our full equation for constructive looks like this. And again, you would just use the one that they're asking for. Most of the time they ask for the smallest, in which case it would be the first. But if they ask for the first three, then you could find the first three. Okay? Alright, let's go ahead and do a problem here. Bye.